Okay, so let's start. It's my great pleasure today to announce our speaker, Professor Anders Hansen, and his list of achievements is very long, and I tried my best to, create a summary so that I'm not consuming the entire talk. And therefore, please excuse me if I'm reading this from the summary because it was carefully selected. So Anders is a professor of mathematics and the head of applied functional and harmonic analysis group within the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. He received the Whitehead Prize in Mathematics in 2019 from the London Mathematical Society and an IMI Prize in 2018 and the Leverhulme Prize in Mathematics in 2017. So, and in 2016, he also won the University of Cambridge nomination to the Rostries Award, and he's also a Royal Society University Research Fellow. He's published at the very top mathematics journals, such as the Journal of American Mathematical Society, and also in the top interdisciplinary journals, such as Nature and the Proceedings of National Academy of Science, which is, I think, is very rare for mathematicians. He's been a PI in several EPCC, European Commission's the Science and Royal Society grants, and also organized recently, actually, 2 6-month programs at the Isaac Newton Institute and 2 high-profile workshops at the Alan Turing Institute. He's been the editor of the Proceedings of the Royal Society, Series A, and also is an editor of Networks and Heterogeneous Media and the SIME Journal on Imaging Sciences. His research spanned many areas, including functional analysis, foundations of computations, artificial intelligence, compressed sensing, where actually Anders has just recently published a monograph on compressed sensing, optimization, operative spectral theory, numerical analysis, computational harmonic analysis, and mathematical signal processing, sampling theory, inverse problems, medical imaging, geometrical integration, theoretical algebras. His recent works exploring computational and fundamental limits of intelligence and optimization sparked major attention, including from engineering, AI, and computer science communities, as is evidenced by a recent IEEE Spectrum magazine paper run about his paper published in March 2022. I'm delighted and excited to hear more about this. So Anders, the floor is yours.
Great. Well, thanks a lot for the introduction. I'm very excited to be here at King College to talk about one of my great passions, namely the mathematics of why things don't work. And I'm going to start by motivating this by showing you some numerical examples. And I'm going to start with this innocent linear program. We all know linear programs very well. And what we're going to do, so we're going to compute solutions to these linear programs, where you see this delta parameter, I'm going to change that. And we're going to compute it with MATLAB's linprog command. And MATLAB's linprog command has a very, very nice feature. It has an exit flag built into it. You see this exit flag gives you a 1 if the solution is certified as correct. And then there's tons of other things that could go wrong, and then you get numbers telling you what has happened. And this exit flag is really crucial because it gives us a trust of the algorithm. So it's okay if an algorithm makes a mistake, but I would like to know it. So now we're going to test this little innocent linear program on MATLAB's linprog. Now MATLAB linprog has built in 3 different types of algorithms that you can choose. You have dual simplex, interior point, and interior point legacy. And what you see here to the left, that's the values of the delta parameter. I know the true solution, so I can check it. The error here is in the L2 norm, and you can see also the exit flag. Now what you see, if I look at the dual simplex, is that in the beginning we're doing pretty well. 0 error, and it certifies the correct solution as correct. Brilliant. But now, eventually, we're getting complete garbage. Not only do we get complete garbage, but we get it certified as correct. And that happens universally for all the other algorithms as well. internal point, slightly different behavior, but the message is the same. Nonsense is computed and certified as correct. Why does that happen? I'm going to show you another example. This is not as innocent as the original linear program. I call it an almost innocent lasso problem. Now, lasso, you may know, is used widely in statistical estimation, image analysis, and more. And what we've done here is slightly different than the linear program. This is a matrix which is centered, and what I mean by that is that the columns sum up to 1. And they're also normalized. This is what statisticians usually do. So the reason why we've done this is that if you plug just in a matrix in MATLAB's lasso command, it will immediately center and standardize it. So we've done that. So this is, we plug that in, this is what MATLAB would actually compute. Okay? And we're going to test this for different values of this delta parameter, as you can see on the slide. Now, MATLAB's lasso doesn't have an exit flag, but it has a warning. That warning will show up when it sniffs that something is fishy. Right? So what I have plugged in here is a 0 if no warning is shown, and then there's a 1 if there is a warning. So it's a little bit like the exit flag, but not as sophisticated. Okay, to the left here, you see the default settings. I haven't done anything. I just click return. I feed it in and hit return. That's the only thing I call lasso. And you see it's a similar behavior to what we saw before. It actually breaks down before, though. So I get actually quite nonsensical results pretty early. And there's no warning. Now, if I try to squeeze a little more out of the algorithm, I'm going to set the relative tolerance to machine precision. It changes. In that case, we do slightly better, but eventually we are starting to get nonsense. The good thing, though, is that now the warning is coming up. It sniffs that something is wrong. But in the end, it gives up and says, well, actually, it might be fine. It's the nonsense. Now I try to squeeze out even more. And I set the maximal iterations to the inverse of the machine precision. Do slightly better. At some point here now, it's simply going to run and run and run, and after 12 hours, we give up. For these values of delta, very quick solutions, and no warnings. So the question is, what is happening? And you see there's two possibilities here. One is that the crew in MathWorks don't know what they're doing. The other potential option is that there's some mathematics of why things don't work that could be lingering in the background. And you would probably think that I wouldn't give a talk about the forward, right? So now we're going to try to analyze this and try to understand it. And we're going to start with linear programming. Simply because linear programming is something that you all know very well, and I know that very well. But it's also a problem that has been investigated for more than half a century, but there's still some really, really delicate open problems. So here it is, as you can see in one of its many forms. I want to point out that I'm not interested in computing the objective function. I'm not interested in that. I'm interested in getting minimizers. I want to have an algorithm that can compute minimizers accurately. And these are different types of problems. The reason why I want minimizers is that that is essentially the basis of modern mathematics and information. Solving complex optimization problems and getting minimizers. I'm going to make an argument for that a little later on. So, linear programming is actually on the list of problems for the 21st century. As you may know, Hilbert created a list for the 20th century, 23 problems. And Smale did the same thing. The 9th problem on his list is a problem about linear programming. So he asks, is there a polynomial time algorithm over the real numbers which decides the feasibility of a linear system of inequalities, and if so, outputs such an X? And then you say, but linear programming, that's in P, right? That is true in the Theorem model. It would be weakly polynomial time. The model that Smale asks for is the blue shoe Smale model. So you assume a real number computer, and you're counting the number of arithmetic operations. If you're a computer scientist, this question will typically be, does there exist a strongly polynomial time algorithm for linear programming in the Turing set? Now, I'm going to talk a little bit about that a little later on, but it's not the importance about the weak versus strong. The issue that I would like to highlight is this. So in the list of problems that Smale has, he writes as follows: but real number computations and algorithms which work only in exact arithmetic can offer only limited understanding. Models which process approximate inputs and which permit roundup computations are called for. Right? And if you're an applied mathematician, you'll say, yes, of course, right? And the issue is that I might be working with irrational numbers on a daily basis. If you're working in signal processing, you might work with the discrete cosine transform. If you work at MRI, you work with a discrete Fourier transform. I will have irrational numbers as input on a daily basis. I can't store them. I will have approximations. But not only that, if you run MATLAB or Python or whatever you do, typically you will be running floating point arithmetic. And that means that an innocent little rational number like 1/3 is stored as a base 2 approximation. The number 0.1 is not stored as 0.1 in MATLAB, it's stored as a base 2 approximation. Right? That means that if I'm running this on my computer, MATLAB or Python, that number will always be an approximation. So the point that Smale makes is that this is not a new model that she just cooked up, prior to the 21st century. This is a model that is the one that would actually see in real life computations. And it's a standard one in computations in general, but it's not always used to analyze things. All right. What do we know about linear programs? It is a true statement that linear programming is in P. It's even here, front page of the New York Times in 1979. Not that many mathematical discoveries end up on the front page of the New York Times. This was a huge achievement. But the issue is this. The statement linear programming is in P means the following. This here is about the Carmarker's algorithm, which is slightly better than the ellipsoid algorithm that was announced in the New York Times. But the as implied results are similar, although slightly better for this one. It says, yes, there does exist an algorithm that can compute linear programs. Here we have polynomial in n is the number of variables, and L, which is the number of bits, or digits, if you will, in the representation of the numbers. Okay? But here's the problem. If I plug in pi here, right, that L is going to be infinite. So if I have an irrational number as an input, the question is, how do we actually solve a linear program then? And I'm not so interested in about that L. I'm interested in K, where K would be the correct number of digits that the algorithm produces. So suppose I want 5 correct digits on my answer. Does L have to be 5? Does L have to be 10? Does L have to be 10 to the 8? The point here is that this result, although as beautiful as it is, does not answer how I work with linear programs if I have some kind of inaccuracy in my input, which I will have on a daily basis. So the question that I'm posing is now simply, given a class of linear programs, and I'm now interested in computing K correct digits, can I find an algorithm that will solve linear programs so that it will compute the linear program with a minimizer with K correct digits, and is it polynomial in n, and hopefully also in K, the number of correct digits? It's a very different question. Okay, so now, so to make this slightly more formal, what this would mean is that I can think about writing this up in MATLAB and I need an oracle for the representation of the number that I'm going to approximate. Think about using the variable precision command as freely as you want. So I can't call pi, that would require an infinite amount of information, but I can get the number of digits from that oracle. Right? So I can call the oracle, I can get 1, 4, 1, 5, and I can't remember the other digits of 5. But if I want 5 digits or if I want 10 to the 8, it doesn't matter. The oracle can give me that. And so this is not a model which is something completely obscure. This is a standard model. If you're a pure mathematician, you might even have seen this. Pfefferman and Clark had a program on computing approximations to functions. There's a series of papers in Annals from the early 2000s. They do this in one of the papers where they do this full extended model, and that is a 150 pages long paper. So the point is that doing the analysis with this model is complicated. And that's also why it is occasionally, or actually I should say, most of the times simplified and not done in the full extent of the model. So I'm not just going to work with linear programs. And the reason why is that, well, I have nothing against linear programs. They're fantastic. There's much more to it. We have semi-definite programs. We have basis pursuit, unconstrained lasso, constrained lasso. And the argument that I'm going to make is that these optimization problems form the core of modern mathematics of information. And the evidence of that is this slide here. I've taken out 4 of the most influential papers over the last 30 years in mathematics of information. What they all have in common is that they rely on computing minimizers of at least one of these problems on that list. And if you add all the citations now, actually I did this about half a year ago, so it could be more than 100,000 now for what I know. But the point is that these are not sort of random problems. I think it's fair to say that they're at the core of modern mathematics of information. Okay. That brings us to the extended Smale's ninth problem. The extended Smale's ninth problem is simply taking Smale's ninth problem and adding this extended model to it, which makes it a quite delicate question. So I'm going to formulate it formally now on a couple of slides. First, I'm going to talk a little bit about notation. I'm going to use psi here. Psi is the solution map, if you will, takes in some input, my linear program, and spits out minimizers. So it's a multi-valued function, hence the double arrows. And this is crucial because my algorithm, I'm going to typically use gamma here for an algorithm. And the point is that I'm not going to ask that the algorithm should be multi-valued. It will always be single-valued. So I'm only asking that the algorithm spits out some die which is close to the set of minimizers. So when I talk about getting k correct digits, I mean this is what I mean by that. Right. Now we can start looking at the actual problem. So the extended Smale's ninth problem, I'm not just going to ask that for linear programs. I can ask that for semi-definite program, for basis pursuit, and so on. Now, suppose I have a class of say linear programs, and the question is, well, I cook up my favorite metric or a norm to measure the distance, and the question now, can I find an algorithm that will compute minimizers of that problem, and the algorithm should run polynomially in k, and n, where k is the number of correct digits, and n is the number of variables. And the answer to this problem here is extremely. So poor you who have to read through this awful theorem. It looks absolutely horrendous. And the reason why it's horrendous is that the theorem states something about a collection of, say, linear programs. And it's true for all of these things, 1, 2, 3, 4, are true simultaneously for that set. So I'm going to read this out to you and sort of explain in layman terms what it actually says. Okay. So let psi, upper left corner, denote solution map to, let's do linear programming. That's the one that we know best, right? So take that. Choose whatever P norm that suits you. That's how we're going to measure the distance. That's how we're going to measure the error, right? Now, choose a integer k greater than 2. The reason why I'm going to choose it greater than 2 will be evident in a second. Now the following is true. I've taken my k. Then there exists a collection of linear programs, omega, so that all of these things are true simultaneously. The first thing it says is that no algorithm can produce k correct digits for all inputs in omega. And even if you randomize your algorithm, you won't be able to do this better than coin flipping. Now, here comes a little bit of a brain twister. If you're a computer science, you will recognize why. Number 2 here says, and this is important, it's the same collection of linear programs. It says that if you allow to boost your randomized algorithm in the following way, you're allowing it to potentially have the probability of non-halting to be non-zero. It could be that it simply just runs forever and it doesn't stay up fast. If you allow that, you can solve all of these linear programs with probability 2/3, but not more. And the reason why this is a bit of a brain twister is that if you're a computer scientist, you're used to, if you can do get a probabilistic estimate that is away for failure that is away from a half, you can just repeat the algorithm, you can repeat it again, you can get it as close as you can to 1. This is impossible. You cannot get better than 2/3. But now, here comes the paradox. 3 here. It's the same, it's true for the same set. If you're a little less greedy, there does exist an algorithm that can compute k minus 1 correct digits. You can't do k, but you can get k minus 1. But this comes with a cost. Any algorithm that can do that will run for arbitrarily long time. Meaning the following, you give an algorithm that can give me k minus 1 correct digits in this. There will exist for any time t, say 50 billion years, an input so that that algorithm will run for longer than 50 billion years to achieve k minus 1 correct digits. And now comes the other paradox. If you're a little less greedy than that, you can't compute k minus 2 correct digits for the same set. That is polynomial time. That is polynomial in m. And what you see here are phase transitions. There's a phase transition from I cannot get k, I can get k minus 1, it's going to cost me an awful lot. And then there's a new phase transition into k minus 2. So you have these phase transitions, and that is also what I'm saying, that the mathematics of why things don't work is also the mathematics of why things do work. It is about being on the right side of the phase transition. Yes.
Clarifying question.
Yes, please.
K was in some sense a parameter, k larger than 2. So I think of k equals 6, and you said that this is possible for k, but it can be done for k minus 1. And then I decided, well, actually, I thought of k equals what another number, and then what's going on here?
So the point is a great question. So I give you a k, then there exists a class omega, so that I can't get that. I can't. So I choose 4, right?
Yeah.
And then so what I'm saying with this is that there's an enormous amount of different collections for which you have different phase transitions with different digits. But it's a very good point. I get this question all the time. So k could be 59. There will be a set omega for which I cannot get 59. I can get 58, but it's going to take a long time. 57 I can do easily. The point is that the world of optimization is full of these phase transitions. That's why things work, and that's why things don't work. You can try this in real life. Take your favorite algorithm and see, get it to spit out the output as it progresses. You can get a problem very, very quickly down to, say, 4 digits, and then start spinning. Try it. Run it for a day, run it for 2 weeks, and it will spin in the 5th digit. That could happen in the 10th. It depends on the input. It depends where you are in this whole zoo of different types of problems. Right. So right now, I would like to say that I'm psychic and say that I know what you're thinking. Because you are thinking that I'm trying to trick you. And I'm trying to trick you by giving the algorithm something which is ill-conditioned. A trained numerical analyst says, this is a conditioned problem. Ill-conditioned problems are hard to solve, right? That's not a hard thing to say. That's true. But I'm not cheating. We're not cheating. Of course, for a linear program, it doesn't make sense to talk about the condition number A because that matrix doesn't have to be invertible. But I can talk about A star. So that's what I'm talking about here. Right? So these are classical condition numbers in the literature, and all of them can be bounded by 2, and this theorem still holds. We're not cheating. These are not ill-conditioned problems, which is a really, really core part. Okay, so the other type of question that people get is, but you've cooked up these really, really bizarre things, right? And you claim that you can see them in real life. Well, this is how we work with mathematics. The counterexample to the quantity required for all is there exists. Okay, I only need to show one bad guy. If that bad guy never shows up in real life, who cares? Okay. So what I'm going to do now is that I'm going to try a basis pursuit, and I'm going to do unconstrained lasso, and the A here is going to be a matrix which is random with IID components from some distribution. And in fact, I'm just going to let M here be 1 to make a very, very simple example. Okay? And I'm going to try this on 2 algorithms. One is SVGO1. SVGO1 is a package that come out from UBC. It's a very, very good algorithm. I really like it a lot. And what we're doing here is that we are simply measuring. So on the y-axis, you see the success rate. Success rate is the number of successes divided by the number of trials. In these experiments, the number of trials is 1,200. And the definition of success is that I've been able to compute 2 correct digits in base time. Okay. And what you see here is now different types of probability distributions used as a uniform. 1, 10, that's the interval. N stands for normal distribution. Here the mean is 1, and then you have the variance to the right. Up there you can see exponential 1 with exponential distribution with lambda equals 1. And what you see is that clearly the probability of failure is not close to 0. In fact, there's an asymptotic behavior. The theorem that I showed you does not explain this, but all of the examples that we construct are constructively made, so it is possible to describe exactly what is happening here. The point that I want to make to you is that it happens, and it happens in front of your eyes. The phase transitions are here. Now, if I change this with different types of distributions, we'll see a different plot. If I change this with a different k, we'll see a different plot. The point is that they're there. Okay. So now I'm going to change a little bit, and I'm going to use some of this framework here to talk about the limits of artificial intelligence. So I don't need to spend a lot of time talking about the success of AI. It's a revolution. It's completely astonishing. And we all agree that it is an incredible revolution. And there's also an enormous amount of optimism. We learned that they should stop training radiologists now. But I do want to point out that it's not that everything is completely smooth with modern AI. There's a debate in the community. There's even, I would suggest, a divide. Ali Rahimi mentioned in his test of time board speech at NeurIPS in 2017 that machine learning has become alchemy. Not everybody agrees with that. If you know about the debate, you know exactly what I'm talking about. If you haven't heard about this, I encourage you to Google it. It's a very fascinating debate that came out of that. The point that I want to make, regardless of you agree with Rahimi or not, one can learn from the alchemists in the following way. So what did the alchemists want to do? Well, they wanted to create gold. How did they do that? Well, they would buy a pot, add a little bit of green, a little bit of yellow, stir, and see, no gold. We can try a little bit of red and stir again. And you can continue this operation as many times as you want. You will never reach goal. But the important part is that that kind of research methodology will never be able to detect its own limitation. You will just continue. You will never figure out that you cannot create goal. So if we're going to actually understand limitations of AI, you need a different type of research methodology. You can't go with the alchemist trial and error approach. And that's where the mathematics of why things don't work is a helpful tool. That's what I'm going to argue. All right. And I'm going to use what people have referred to as the Achilles heel of modern AI, that it is universally unstable and hence in many cases untrustworthy. I'm going to show you a couple of simple examples before we get into the theory. Right. So here's a paper. It's published in Science in 2019. The important thing that I would like to highlight is that this is a paper which is written not by grumpy mathematicians like myself, but by people in the medical profession. So these guys know what they're talking about from a medical point of view. This is a study led by Isaac O'Hain, who was at Harvard Medical School. And it's a paper that really illustrates some of the delicate issues. The one you see to the top is an example of automatic diagnosis in medicine. You're trying to do cancer detection and early detection of skin cancer. So you train a neural network to figure out if a mole is benign or malignant. And to the very left, you can see that it's very confident that this is benign. Excellent. Fine. I go home and I sleep sound. You can add just a little bit of noise to that so that the human eye cannot see the difference. And now the AI is becoming very confident that this is malignant. And the problem here is that one of these is obviously wrong. But how can I trust it? The real delicate question is it actually possible with an algorithm to determine which of these guys are correct? Now, you can see tons of this, and if you Google it, you can Google instabilities and deep learning, there's tons of them. Here's one where you can do rotation, you can see this in text analysis, you can do this in sound, so on and so forth. And the message is quite uniform. We have these instabilities that lead to this potential untrustworthiness. Ooh, can you see here? It's not great. Oh, it's not. You can see it. Can you see what's going on here?
There is something in there.
Maybe you can turn off the light. No, it's okay because the point that I will make is actually on the screen is really great. Oh yeah, sweet. Thank you, sir. Very helpful. So this is when AI is used for speed up in MRI. So MRI is very time consuming. And so what you do is that you train a neural network to take the Fourier information that comes from an MRI scanner, and it reconstructs the image. And you can get really, really good accuracy. So here's the original, and yeah, in an ideal world, we would have seen how sharp it is. But the problem is this. It ends up putting an hallucination in there. And this hallucination has absolutely nothing to do with the anatomy of the person. But it could very easily fool a radiologist. So you're essentially getting a detail which has nothing to do with it. But it's very hard for a radiologist to determine that, oh no, this is not unphysical. So this is an AI-generated hallucination, as it's called. Anyway. So the limits of AI is not something that is only for grumpy mathematicians like myself to study. This is becoming mainstream now. And I want to point out, so IEEE Spectrum is the flagship of IEEE. It self-identifies as the world's leading engineering magazine. And they write a lot about AI. In their December 2021 issue, they had a summary of the main stories of AI that they covered. And what they point out, I'm going to read out here, 2021 was the year in which the wonders of artificial intelligence stopped being a story. And it continues, many of this year's top articles grappled with the limits of deep learning, today's dominant strand of AI, and spotlighted researchers seeking new paths. So the point is that this is not sort of a fringe thing now, it's becoming popular. Not only that, it is becoming a legal issue. You may know that the European Commission is trying to iron out a legal framework for regulating AI these days. And that's not simple. So we learned that in the light of the recent advances in artificial intelligence, the serious negative consequences of its use for EU citizens and organizations have led to multiple initiatives from the European Commission to set the principles of trustworthy and secure AI. And we learned that robustness, security, and accuracy are really crucial in these high-risk areas that we define. And here is the paradox. Because if you're a mathematician, it is likely, and you're doing AI, it's very likely that you've heard of the universal approximation theorem and all the variations of that and its cousins. And basically what that says is that you can do whatever you want with neural networks that you can do with a continuous function. So in layman terms, it really says that if you have a problem which is stable, you should be able to approximate that with something which is accurate and stable mathematically. You can write down the proof on the blackboard. They do exist. So why don't we find them? We universally don't find them, but they do exist. And in fact, we're using that kind of theory to suggest that it should work. But it really doesn't. And the question is why? So, now I'm going to ask a slightly more formal mathematical question. Suppose now that I have a collection of data, and I have a problem. And I can show that there exists a mapping that can take that data to a neural network that's going to do the job for me. So suppose I can prove that, and give you a proof of that on the blackboard, right? I have data, I have a mapping that takes the data to the desirable neural network. The question, can I compute it without the obvious? And can I compute it to a desirable accuracy? So now I'm going to show you a theorem which is related to the previous theorem. And we're going to use some basic optimization problems. We could have used much more abstract mappings to show this theorem. We want to use this because you can see the mapping in front of your eyes. So I'm going to take these three problems, P1, P2, P3, and then I'm going to ask, can we find a neural network that can solve these problems? Okay? And then I'm going to ask, can I find a data set so that I can find a mapping that takes that data set to the good neural network that's going to solve the problem? Okay? And then I'm going to ask, can I compute that good neural network? So when I say train in real life, I mean that literally. So that means that the input that I'm going to have, so up in the left corner, I'm going to have an A, that's the matrix, and then I'm going to have a bunch of Y's, that's going to be the inputs, and then I would like to get minimized results. But if I'm going to implement this on a computer, I can only see approximations to them. So I can see approximation to the Y's, approximation to my M, and approximation to the solution, but to whatever accuracy I want. And that's my training data. And now I'm interested in, can I find a mapping that takes that data to the neural network that's going to do the job? And then we're going to ask you about the computer. So the first theorem, and this is not in any way dramatic. We do not claim that we are doing something fantastic to show this. This is pretty straightforward to show that for these problems, for these kinds of data, there exists a mapping, we call it kappa here. It takes the training data to the good neural network that gives me the solution to the problem. Excellent. It does exist. But how do I get it? And now I'm going to show you this theorem here, which is very similar, but still very different to the other theorem. Because not everything is about data. Okay. So choose a K, it's going to be the accuracy. And then choose L. Can you see L there? That's going to be an integer, and that's going to be the number of data that we're going to be interested in. Okay? arbitrary k, well, greater than 2, arbitrary L, right? So now what we learn is that for that k and L will exist a set of problems. And I know that there exists a mapping that takes exactly that training data to the good neural network, but you won't be able to compute k correct digits. If you're a little less greedy and you want k minus 1, you can get it, but with high probability, if you run your stochastic gradient descent algorithm or any probabilistic algorithm, you will have to use arbitrarily many data points to get there. But if you're a little less greedy again, you can solve the same problem with just L training data. So you see these kinds of phase transitions, not just with accuracy, but also with training data. And this, to summarize, you can summarize this with these two figures. This is the world of neural networks. You have the ones that you can show exists, but you will never be able to compute them. Then you have the ones that you can compute 1 digit, 2 digits, 3 digits. There are neural networks that you can compute arbitrary digits. But not only that, you need to discuss the amount of data you need. That's this figure here. This is sort of the true world of neural networks. So now the upper green part there, which is separated by the upper red, that will be the type of networks for which I can compute to arbitrary accuracy with only 1 data point. And then you have phase transitions in between all of them. So there is a very, very delicate world of neural networks for which you can compute. Some of them you can't, and some of them you can. And the issue is the amount of data. Please, yes.
I'll clarify quickly.
Yes.
You're saying trainable with 1 data point?
Yes.
Means there exists the data point which would train it.
So the point is that, exactly. So so in the construction we have, there's my omega, which is the class of training data. That can be big, and I don't necessarily need to use all of them. So there will be certain cases for which I only need to take 1 data point, and then I'm good. And then there will be other ones for which I need 59 to get, say, 3 digits. And the whole world is essentially separated by these types of phase transitions. And the bottom line that I want to get through with this is that the universal approximation theorem is absolutely fantastic. There's nothing wrong with that. But it doesn't describe the world of neural networks that you're going to code up on a computer. The neural networks that you're going to code up on a computer is a tiny little subset of that gigantic world of neural networks that you can prove exist. Okay, I need to wrap up because I'm running out of time. Here's the paper if you're interested in it. In the title of the talk, I mentioned what is referred to as the Solvability Complexity Index hierarchy. And I just want to mention this because this is a part of a much bigger program on foundations. And this is a paper that was written more than 10 years ago and had nothing to do with AI or optimization. But this kind of program that we're working on actually provides a lot of tools that are very handy for showing things in wide collections of the mathematics of why things don't work. And while this might be a little bit of pure math mumbo jumbo, it's not something that the engineers seem to shy away from. So we were a bit surprised and quite pleased that these results were picked up immediately by the engineers. And we were also a little proud that they actually launched this and publicized it. So it's not something which is just of curiosity for mathematicians. I just want to show you a couple of other papers in case you're interested. The upper one there is on the archive, and we wrote a paper in Science News in October. This is with Des Hayem and also Ivan here. We call it Deep Learning What Could Go Wrong, and we hope that that's a reasonably sort of easy to understand overview of some of these issues if you're interested. Okay, but I have about 5 or 10 minutes. So I'm going to end with 2 final questions. And that is, the first one is, do algorithms fail? Well, the answer to that is yes, we know that. A slightly deeper question is, can we determine when we're wrong? And that's much deeper. And this is, we're going to talk about optimization problems. But this question here is much deeper, not just about optimization problems. It really goes to the core of potentially curing the issue of untrustworthiness in AI. When can you check if an algorithm is wrong? I don't mind having algorithms that are wrong. I just need to know when they're wrong. So I can have an algorithm that can potentially spit out complete nonsense. If I know that, I'm just going to discard it, fine, and move on. And when it's right, it's great. But I need to know it. So I want to show you this experiment again. What we have on the left here, that we can explain with the first theorem that I showed you. But it does not explain that. Because having an exit flag does not imply having an algorithm that's going to work. It will just tell me that that algorithm fails on that input. It doesn't suggest, oh, now you're going to change the input, the output to that. It just says, you're wrong. Okay? So having an exit flag does not imply that you can solve the problem. It just says, I can know when I'm right and I can know when I'm wrong. Okay? And you see, this is actually pretty serious. And this is not a mathematics thing. You can try this with MOSEC or some of the really expensive software packages for optimization. They will have exit flags and they're going to fail. The question is why, and the question is also, can you solve it? Is this just because they don't know what they're doing, or is this an algorithm? So I'm going to ask, can the exit flag be computed? And I just want to point out before I show the theorem, is that you can very quickly make this problem here completely trivial. And we're not interested in that. So I'll give you an example. Suppose you're going to have an algorithm that's going to solve linear programs, and I'm supposed to design an exit flag algorithm for that. And your algorithm spits out Mickey Mouse all the time, right? It's very simple for me to write a program that says, if Mickey Mouse, exit flag equals 0. Right? That is super trivial. So I need to require that the algorithm that I'm going to check is going to spit out something which is what I would expect. So I'm going to assume that there's an alpha, and that the algorithm spits out something which is close to the range. It doesn't have to be correct, but it can't spit out Mickey Mouse. It needs to spit out a vector. That should be, within the range of the original problem, because otherwise it becomes trivial. So, in the interest of time, I'm going to be a little quick with this theorem because it's long and horrendous. But what it really says is that, in short, you cannot compute the exit flag. That may not have been a great surprise given the lead up. But there is an interesting thing here, and that's number 3 here. The problem of computing the exit flag is strictly harder than computing the original problem. So there's absolutely no way. And what that means is that, what MathWorks tries to do here is actually impossible. That doesn't mean that they shouldn't have an exit flag. But the exit flag will either certify correct things as wrong or certify wrong things as correct. So, we will eventually tell MathWorks that what they're trying to do is actually not possible. But right now it's great because it's great motivation to show that they fail. So if you work for MathWorks, don't tell your boss yet until the paper is published, all right? If they read the paper, they can do whatever they want. But what they're trying to do is impossible. And then I'm going to wrap up because I had in the title, the mathematics of why things don't work. And of course, this is a program that is not something that we start. This is the essence of the foundations of mathematics. And everything started with Hilbert. So Hilbert was convinced that mathematics was the ultimate language for the sciences, meaning that you could prove or disprove any statement with mathematics. And he had a firm belief that algorithms could solve all problems. And that is shown typically in his formulation of the 10th problem. It's not a question. It says, define an algorithm to determine whether a given polynomial Diophantine equation with integer coefficients has an integer solution. And as we all know, what happened to Hilbert's program was that the ultimate party poopers of the century, Gödel and Turing, really contributed an enormous amount to the mathematics of why things don't work. So this is a program which is just a continuation, and some of the techniques that we're using date back to Gödel and Turing, and they should of course be credited with the incredible stuff that they did for this. And as we all know, it took about 7 years to figure out the solution to the 100% problem, and now that is not controversial in any way. No algorithm exists that can solve the equations. It's a famous non-computable problem. And this is at the heart of the mathematics of why things don't work. I also want to mention Smale. Smale has had an incredible program on the foundations of computational mathematics. And on his list of mathematical problems for the 21st century, the last one, 18 on that list, is actually what are the limits of artificial intelligence. So what we're trying to do here is simply continuing this path. And if you're interested, I'll be very happy to talk about this thing. You can see that I'm passionate about this, but it's also not just a pure mathematical exercise. It is to try to get an understanding of modern AI. Just if you're interested in the papers, the top one is on the extended Smale problem. That's the first theorem, and the last one on the exoplan. I mentioned this one here, that some of the foundations are. This is the other paper with the limits of AI. And I just want to mention a couple of other papers, because this links also to some of the work by Frank Mellon in the 80s. And if you're interested in, there's also a science newspaper coming out now in May. And I'm going to end with some completely shameless self-promotion. We have a book out. Hope you love it. And thank you so much for your attention.
I was wondering whether some of this functionist is roughly showing his complexity.
Yes and no.
Yeah,
Yes, exactly. So it's a great question. The reasons why you can't compute them has nothing to do with that, but they will show up in the cases for which you will have restrictions on what you can approximate, and that's really important. So in that case, you will have a guidance on which types of functions you can do. But you can, there always exists, some other neural network that can do it. But given these restrictions, it will tell you, okay, this is the class you can do. So they are, what should I say, morally connected, but mathematically still far apart. But it's a very good point. So, just as much as you need the existence theorems for saying that neural networks can exist, you need that kind of restrictions to understand theoretically. But there will potentially even be cases there for which you say, okay, within these restrictions, there exists a neural network, and someone can say, that's all well and good, but you won't be able to compute it, say, to more than 4 digits. So it's a very valid point.
I got a simple and naive question on this. Are you saying we are all doomed?
No, not at all. And I'm not claiming that these sort of negative results will tell you exactly everything that fails. It just suggests that there's a paradox between the mathematical theory that says that they do exist, and that we need to be able to understand which ones you can compute. So what we're trying to say here is not in any way that you shouldn't use AI or shouldn't do AI research. It's incredibly important, but there are delicate issues for which the mathematics of why things don't work is going to be essential. And it may not be a great surprise that these things show up, because we've seen from the foundations of mathematics that they show up over and over and over again. So that they also show up in AI is in some sense expected. The question is which way they show up. So we just need to have a theory for which not just says something about which neural networks we can approximate with certain conditions, but when there exists an algorithm that can do it as well. And then it's up to the whole community to figure out how this works. We're only saying that this is a very delicate classification theory, and let's start work on it.
So just to check if I right or wrong. So basically, your previous first algorithm, you were saying that we can kind of bound more or less what we can learn with the Hilbert system, etc. But in your last algorithm, you said, okay, but if you want to get a level of confidence,
Yes.
you have no confidence or how much confidence you can get.
Exactly.
So basically, the extrapolation would be like we need to do a very hard work just to bound all. I mean, that's just the boundary and all the things that we can say about the algorithm. And
Yes.
even in that case, we won't be
Exactly. So trying to figure out when this is trustworthy is extremely hard. That doesn't mean that they don't exist, though. So I'm just going to give you a very simple example. There's a paper in Science published in 2017 for which we want to compute the ground state energy of a Schrodinger operator. This is what the computational chemists do on a daily basis. Theoretically, it's not that hard. Practically, it's incredibly hard because of the dimensions. So somebody says, why can't I just try to write this as an optimization problem? I have H, if that's the Schrodinger operator Hamiltonian. I have an inner product, HF, F, min over all F's in L2. Write that F as a neural network and optimize over the weights. And here's the crux. If you compute such a function, I don't care how you got it. I can plug that into the inner product, and that will always be an upper bound. I will not make any mistake. So if somebody said, okay, I have an upper bound for the ground state energy of that thing, which is 39. You go and train your neural network, and I don't care how you did it, and you plug it in, and now suddenly you get 11. I can't argue with that. That is a way of checking. It's a very simple example, but there do exist problems for which you can use neural networks, you can use standard optimization, and you really don't need to know what you're doing, as long as you can check. This is a very simple example of checking, but it's not trivial. Even though this is a trivial example, it's very, very useful, because it suggests now that you can do things in much, much higher dimensions than you can do before, and you can check it. So this is a counterexample to my example. In this case here, you can make it trustworthy. Absolutely. But how to do that in general is extremely difficult. So we already know that there are cases for which I can make AI trustworthy, but there are not many of them that we know still. So the negative results don't say that, oh no, you can't do it. It just says that it's going to be very difficult. So let's wrap up and see what we can do. That's sort of the gospel.
Sorry, can I ask a very mundane, amateurish question? You mentioned that artificial intelligence has made extraordinary advances. I don't see that. I mean, what I see
Yes.
as a mundane person,
Yes.
Boston Dynamics shows us extraordinary robotic advances.
Yes.
They can look like humans. But I try and talk to Siri, and it can't cope with a single. It can't do anything. It is useless, and it does not seem to have advanced in the last 15 years or 10 years, as far as I can see. What's happened? Why don't we see useful, intelligent, interaction at that level? At least is what you're describing. Is there something stopping it advancing?
That is a great question. And okay, so my personal belief is that training neural networks the way we're doing now is probably not going to lead to the actual AI. That's my personal belief. I could completely be wrong about that. And essentially, my opinion is just an opinion. Do I think that there are problems here that will hinder this? Yes, I do. Can I, with these theorems, say that you will never, with this methodology, be able to create something which is truly intelligent? No, I can't. But I can point towards hurdles that are completely non-trivial, and also helping, in some sense, guiding us in the somewhat trial and error-based research methodology. We can just think about what the how alchemy would have looked if they knew that they couldn't create gold with that. With their approach, or with any approach. So if I can answer the question, why haven't we reached further with this? No, I must say I cannot prove that, but I do think that there's a link, and I hope that we can potentially, with more understanding, and by also understanding the limits of II in general, being able to guide in the right direction. And I completely agree with you. And some of the quotes that I have shown in the slides do not necessarily represent my personal view. I am not a huge fan of firing all the radiologists, for example. But I do point to them because these are not provocative statements that are made as jokes. These are serious claims. So yeah, it's a great point, and this would require hours of discussion. And in some sense, my opinions will simply be opinions. I simply cannot prove things yet, but we can at least try to guide. I think there was a gentleman, yeah.
Yeah, thank you so much. That's very interesting. Yeah, maybe the question doesn't make sense, but you tell me then. So I was wondering if you would allow sort of continuous time algorithms, like you do some sort of gradient descent and you idealize it, like you write it in continuous time. I understand that it's idealized and probably it's also difficult to quantify computation effort. But would some of the story then still be the same, or would some problems disappear? I mean, I guess I'm asking because you started with the discrepancy between discrete and continuous.
Yes, it's a great question. The answer is yes. In certain cases, some of these phase transitions will be different, and in some cases they won't be there. Many of the times, but not all of them, these phase transitions will happen exactly because of the discrete versus continuous. So, from a philosophical point of view, if you can hook up potentially an analog computer that can beat the church Turing thesis, you will also beat some of these phase transitions. But that is subject to you actually break the church Turing thesis, which suggests that anything that you can do physically in this universe now is untrue. So it is a very valid question, and it's very deep, but within the realms of computations now, these theories will describe what you're doing. If you can boost this and create a computer that can compute truly over the rails, then things might change. Yes, but not everything though. Some of them will still be. There are still certain things, but some of these spatial systems will not have. Sorry.
Yeah, you mentioned that it was difficult to compute the exit flag
Yes.
for the software packages like Mosaic and MATLAB.
Yes.
I'm curious to know if you have a thorough understanding how they compute their exit flag.
Yes.
If it is robust or not.
Yeah, no, it's a great question. Okay, so how they do it. So let me go. Okay, so first of all, MATLAB is not fantastic at documentation. Let's go back. Right. No, this is what. So some of these things are simply that you can check them. So I could run my algorithm and I end up with a not a number, right? In that case, I just halt and say I give up. So many of these are flags for which there's really something. You have a for loop and a while loop and something like that, and there's something going wrong, and it just gives me a flag, right? When they actually give you a 1, I don't know what that mechanism is because it's wrong. So I'm not suggesting in any way that they should give a pattern an exit flag, but they can't give it a 1. So as I said, the exit flag will either give you wrong certifications of something that's correct, or it will give you correct or a classification that is correct when it's wrong. And then you can ask which one's worse, and I would argue that you should always have a pessimistic exit flag, meaning that there will be certain things that are correct, probably will say, I don't know, or it's not correct. So what I would say to math is you can keep all these other things here that really tells me when things are wrong, but when you get a 1, you can't promise, on your life that this is true. That is impossible. So what it should be a list of all these other things that can go wrong, and then when you get a 1 there, it shouldn't say function converged. It should say I have no idea if this is correct, but this is the best I can do, and that will be a correct statement.
Yeah, but we don't know what is inside their code, how they code this exit flag, or what they use come up with it.
Yeah, so what I'm saying is that many of these are simply checks, right? That you say, okay, if I get the noun, then it's okay, here's the output. What it actually does, because if you look at the interior point method, for example, it's unclear to me why the interior point method and interior point legacy use different things. This I understand because this is an interior point method, this doesn't make any sense, this makes total sense. But the documentation is not right. So MathWorks, if you watch this, keeps your documentation. So I just assume that when they certify, just plug it in and say, here's the criteria. But that has nothing to do with the minimizer. That's the whole problem.
Okay.
So there will be umpteen different ways of doing it, but what we're saying is that regardless of what you do, you will have exit flags that are going to fail. So don't give up exit flags, but don't essentially sell your stuff with a certain thing. That is not possible and shouldn't be done in commercial software. That's not possible.
And I have again, a naive question. So yes, I think I learned that software, like one that involves optimization, like that type, is not certifiable, which again, is certifiable. And I believe that those counterexamples which you presented with the exist set of problems which are, nasty, like we cannot imagine about them. Do you have a feel of how broad this set of problems may potentially be? Because you just gave us here they are, but I'm sure there are other.
Absolutely. So this is a great question. So I wanted to show you these numerical simulations here to suggest that there's much more. And some of the tools that we provide can help assisting here. But this is just certain cases that we have coded up and we can say something about. But these phase transitions will happen in other areas as well. And the whole point that I also want to make, that the mathematics of why things don't work is also mathematics of why things do work and with which probability. So the point here is that this is just a beginning, and in some sense we're not done, and we're just saying, why don't we just collectively try to figure this out? But you will see the phenomenon. So if you're running something and it's a random matrix and you wanted to compute a minimizer, or you're doing this in some kind of AI, it could very well work. But we need to know why and how. And it could be a phase transition. And if you're on the right side of the phase transition, everything is fine. And another thing that's important to get through is that it's the precision that is needed for the application which is crucial. So if I'm going to produce an image that a radiologist are going to look at, what is the precision that I need? I'll do the following example. Take an image, your favorite image, which is displayed in MATLAB, black and white, okay? And zoom in on it to pixel level, right? So it's a number between 0 and 1 with digits, okay? Take that pixel, zoom in on it, and try to change the value in the 4th digit. See if you can spot the difference. This is not a universal test. It's something that I simply do at home. You can try it yourself. I cannot see the difference on the pixel value by changing the 4th digit, right? So it's unlikely that a radiologist can give me a different diagnosis if I have changes in the 4th digit. He or she will not be able to see a difference. And that means that 4 digits is completely fine. We don't need to fight for 5 or 6 or double precision in that case. So then we need to figure out, okay, can I get 4 digits? Then I'm safe. But in another area, it can be completely different. I need 15. And if the phase transition says you can't get that, but you can get 12, okay, then it might be an issue. So this is really also a key problem to emphasize. But this is just the beginning. So please join in if you're inclined.
Maybe nice question. What about the distribution of the data set that you use? Because for example, you have the result that you show was a fixed data set.
Yes.
So
yeah.
Let's say that if you want the position of the transition,
yes,
might depend on the type of data. Even
absolutely. Yeah.
Okay. So I can have, for example, 0 measure for some subset. Absolutely. If I tune my data set.
This is a great question, and this is not trivial. This is a very, very good one. And the purpose of the theorem is to show the effects. So we say that the paradox is called, there exists a mapping that can take the data to the good guy. So if I just said, there exists a guy out there that can do the job, you would say, yeah, okay, great, but I need to have some data that's going to give me that guy, right? So I show that there's data that can give me the guy, but I can't do it. And you could perfectly valid question to say, oh yeah, but you know what, I'm going to change that a little bit. I'm going to have a random distribution. What happens now? Absolutely. What I'm saying is that there are examples for which this can happen, and then we need to figure out in which other cases. So do the same thing as we do here, put a probability distribution on it, and see what happens. That's not simple. But at some point, you know, we have to start with the counterexample.
Yeah.
It's like Turing says, okay, there are problems for which you can't compute. Here's the halting problem, and then you go on from there. And the point is that if you look at the history of foundations in computer science, a negative result does not stop people from doing computer science. It grows an incredibly sophisticated theory out of it, and then you start to understand. But you know, it's the quantifier issue. You know, it's the for all and there exists. So we show here's an example, and then we need to have the classification here. But your question is not naive. This is a very, very good point. And yeah, we're just talking about the beginning.
Question? If not, we thank Anders for this.